Black holes are the most extreme objects in the universe, regions where gravity is so intense that not even light can escape. The closer we look, the stranger everything becomes. These are 10 of the most disturbing things scientists have found near them. Number 10. Sagittarius. A star is never still. At the center of the Milky Way, 26,000 light-years from Earth, sits a supermassive black hole, 4 million times the mass of our Sun. It is called Sagittarius A star, and in 2024 and 2025, NASA's James Webb Space Telescope revealed something unexpected. It never stops flickering. Using Webb's near-infrared camera, a team led by Northwestern University astrophysicist Farhad Yousefzadeh observed Sagittarius A star for 48 hours across an entire year. What they found was a continuous chaotic light show, 5 to 6 major flares per day, with dozens of smaller bursts in between. Every observation session was different. No pattern, no rest, no stable state. The flares come from the accretion disk, superheated gas and plasma spiraling inward, producing violent outbursts of radiation. Two separate processes may be responsible: turbulent disturbances in the disk creating small flickers, and magnetic reconnection producing the larger eruptions. Number 9. Quasars, black holes brighter than entire galaxies. A quasar is what happens when a supermassive black hole feeds aggressively. Gas, dust, and entire stars fall into the accretion disk, heated to billions of degrees. The resulting radiation outshines everything around it. A single quasar can outshine every star in its host galaxy combined, hundreds of billions of stars, by a factor of up to 1,000. The most extreme example known, J0529-4351, identified in 2024 as the brightest quasar ever recorded, is consuming the equivalent of 370 solar masses of material every single year. Its accretion disk spans approximately 7 light-years across, one black hole, feeding, generating more light than 1 trillion suns simultaneously. Quasars are found mostly in the distant universe, meaning we see them as they existed billions of years ago, when black holes fed more voraciously. The implication is that every large galaxy, including ours, once hosted a quasar. The Milky Way's own center was almost certainly one of them. Whatever was near it then did not survive. Number 8. Relativistic jets, beams that cross millions of light-years. When a supermassive black hole accretes material, magnetic fields in the accretion disk can channel infalling matter into 2 narrow beams, firing outward from the poles at velocities approaching the speed of light. These are called relativistic jets. The jets from Galaxy M87 extend approximately 5,000 light-years from the black hole. In the most powerful active galactic nuclei, jets extend for millions of light-years, crossing distances that dwarf entire galaxies. The energy driving them is partly gravitational and partly extracted directly from the spin of the black hole itself through a mechanism called the Blandford-Znajek process. When a relativistic jet is aimed directly at Earth, we call the source a blazar. The entire energy output appears focused at our instruments. Some blazars are visible from billions of light-years away, a beam of energy traveling at near light speed, powered by a spinning black hole, crossing millions of light-years of space. It is one of the most powerful continuous processes in the observable universe, and it is happening in thousands of galaxies right now. Number 7. Rogue black holes, wandering invisible through the galaxy. Not all black holes sit quietly at galactic centers. Some are moving through the galaxy alone, invisible, and nearly impossible to find. In 2022, astronomers announced the first confirmed detection of an isolated stellar mass black hole drifting through the Milky Way. Using Hubble and gravitational microlensing, the bending of background starlight, by a massive object passing in front of it, they identified an object with roughly 7 times the mass of our Sun, moving at approximately 45 kilometers per second through interstellar space. No companion, no disk, no light of any kind. Black holes form when massive stars collapse. Those stars form throughout the galaxy. When they die, the resulting black holes inherit the star's velocity, sometimes amplified by the asymmetric kick of the supernova explosion, and continue moving through space, dark and silent. Estimates suggest the Milky Way contains up to 100 million stellar mass black holes. The vast majority are completely invisible. They drift through the same space our solar system travels through, unseen, uncatalogued, and essentially unmappable with current technology. Number 6. Accretion disks, matter moving at half the speed of light. When material falls toward a black hole, it spirals inward, forming a rotating disk of gas and plasma. And what happens inside that disk is unlike anything else in the universe. The inner regions of an accretion disk reach temperatures between 10 million and 100 million degrees Celsius, far exceeding the surface of our Sun. At these temperatures, the plasma radiates intensely across the X-ray spectrum. Material in the innermost stable orbit moves at a significant fraction of the speed of light. For a rapidly spinning black hole, orbital velocities can approach half the speed of light. The disk is not smooth. It is turbulent, threaded with intense magnetic fields, prone to instabilities that generate sudden outbursts. It is the direct cause of quasar luminosity, relativistic jets, and the flickering of Sagittarius A star. Almost everything strange we observe near black holes traces back to what happens in this disk. Number 5. Gravitational waves, the sound of colliding black holes. On September 14, 2015, the LIGO detector registered a signal lasting 0.2 seconds. It was a distortion in spacetime smaller than 1/10,000th the diameter of a proton. It was the sound of two black holes merging. Two black holes, each roughly 30 times the mass of our Sun, had been spiraling toward each other for hundreds of millions of years. In their final fraction of a second, they released more energy in gravitational waves than all the stars in the observable universe emit in light during that same moment. The missing mass. The difference between the two original black holes and the final merged object was converted entirely into the energy of gravitational waves, rippling outward through spacetime at the speed of light. This confirmed a prediction Einstein made in 1916, but never expected to be verified. Since then, LIGO and its partner detectors have recorded dozens of black hole mergers, each one a snapshot of the most violent events in the universe, arriving at our instruments as a whisper barely larger than nothing. Number 4. Primordial black holes, relics from the first second. Stellar mass black holes form when stars collapse. But there may be a third category that formed before any star existed. Primordial black holes are hypothetical objects that may have formed in the first fraction of a second after the Big Bang, when the universe was so hot and dense that random density fluctuations could cause direct gravitational collapse. Before any star, before any galaxy. Their predicted mass range spans from lighter than an asteroid to millions of times the mass of the Sun. Some theoretical models suggest primordial black holes in a specific mass range could account for a significant fraction of dark matter. No primordial black hole has been directly confirmed. But they have not been ruled out. The unexpectedly high masses of some black holes detected by LIGO, the presence of supermassive black holes too early in cosmic history, and patterns in the cosmic microwave background all have primordial black holes as a plausible explanation. Objects from before the first star, possibly surrounding us, completely undetected. Number 3. Dark matter spikes around black holes. Dark matter makes up roughly 27% of the universe's total energy content. It does not emit light, reflect light, or interact electromagnetically. We know it exists only because of its gravity, and black holes may be surrounded by it in extreme concentrations. When a supermassive black hole forms at a galactic center, its gravity draws dark matter inward over billions of years, creating a density spike, a region where dark matter concentration reaches orders of magnitude above the surrounding galaxy. Where dark matter is dense enough, particles may annihilate each other, producing gamma rays. Some studies of the galactic center have reported an unexplained gamma ray excess consistent with dark matter annihilation near Sagittarius A star. Others attribute the same signal to a population of pulsars. The question is unresolved. If dark matter spikes are real, black holes are not just consuming ordinary matter. They are surrounded by, and potentially interacting with, a completely different kind of matter that physics still cannot directly detect or explain. Number 2. M87, the first real photograph of a black hole. On April 10, 2019, the Event Horizon Telescope collaboration released an image of a glowing asymmetric ring of orange and gold surrounding a dark central shadow. It was the first direct photograph of a black hole's event horizon, the shadow of the point of no return cast against the bright infalling plasma. The black hole is M87 star, 55 million light-years from Earth, with a mass of 6.5 billion solar masses. The Event Horizon Telescope is a network of synchronized radio observatories spread across the entire planet, from Hawaii to Chile to the South Pole, linked together to function as an Earth-sized telescope. The resolution required to image M87 star is equivalent to reading a newspaper in New York from a cafe in Paris. The image confirmed what general relativity predicted. The size and shape of the shadow matched the theoretical calculation almost exactly. The ring is asymmetric because gas on one side moves toward us, brightened by relativistic effects, while the other side recedes. Number 1. Spaghettification. Of everything that happens near a black hole, spaghettification is the process that most directly demonstrates what extreme gravity does to matter, and to anything made of it. It is not a metaphor, it is the actual term physicists use. Gravity weakens with distance. Near a black hole, this gradient becomes extreme. If you were falling feet first toward a stellar mass black hole, the gravitational pull on your feet, closer to the singularity, would be incomparably stronger than the pull on your head. The difference in force across the length of your body would stretch you violently, simultaneously compressing you from the sides. Your body would be pulled into a long, thin strand of atoms, elongated beyond any structure's ability to hold together, until you were reduced to a stream of individual particles spiraling into the event horizon. For a stellar mass black hole, this happens before you even cross the event horizon. For a supermassive black hole like M87 star, the tidal forces at the horizon are gentler. A human body could theoretically cross intact. The spaghettification happens later, closer to the singularity.